Hello. In this section, we're covering 12.5, Equations of Lines and Planes. And there's a lot to this section, but really in the end, there are just a couple of things that we need to get a line and a couple of things that we need to get a plane. But first, I want to talk a little bit about what makes this such a big deal, right? So when we were dealing with 2D and we needed the equation of a line, we could just get y equals mx plus b and everything was great. The problem is that if I gave you an equation like y equals mx plus b in 3D, then what's going to happen is that's going to be a plane. It won't be a line. Okay, so there actually is no way for us to get a line in a three-dimensional space without using vectors because a line is a two-dimensional item. It's flat, right? It just goes left and right or up and down, but it doesn't have a third dimension to it. So we have to do some work. One of the things that has to happen is we're still kind of aiming for the same sort of form of like some name, we're going to call it R of t, is equal to some initial point plus a variable times a slope. But in 3D, we have slope in three different directions. And so that's like a vector. And a vector can give us slope in the x direction and the y direction and the z direction. So the vector that we're after is actually called the direction vector. And another name for it, you could honestly kind of call it the slope vector for a line in 3D. So we're going to need that vector. And the reason it's called a direction vector is because if you know the slope in the x direction, the y direction, and the z direction, you're going to have your line pointing in the right direction. From there, we also need a point. So right here, I've got this point on a line L, and there's a vector, this red vector, it's called R naught. And R naught is a vector that points at a point on a line. So it's also kind of weird. Like if we want to find like a way to represent a point so that it's a vector, we can just switch from parentheses to angle brackets, and now we call it a vector. Sometimes one of the definitions of a vector that is used is a pointy stick that just points at something in space. And that's actually exactly what it is. A vector points at something. There might be nothing there. In this case, we're hoping that our vector R naught is actually pointing to a point on our line. And then there's this R vector that's pointing to some other random point. It's actually like an unnamed point. It's just X, Y, Z. Okay. And that's to get the variables involved in our problem. But for us, our variable is actually going to be t. So yeah, we'll see how that works. Okay. And then the last thing is this v vector right here. I'm going to highlight it because it's going back to the whole direction vector thing. So notice that v, if you compare it to the line L, they are parallel. So v just points in the same direction as our line. It's not actually even on our line because our line is randomly in space, okay? All the vectors that we have are position vectors, so all of them start at the origin. R naught points at a point on the line, a specific point. R points at a general point on the line, and V doesn't point to the line at all. V is just parallel, and it is called the direction vector. Okay, so, in this little blurb here, we're saying if your direction vector, V, has components A, B, and C, And you have an initial point R naught, and you've got some X naught, Y naught, Z naught values. They're actually numbers, okay? We're just using X naught, Y naught, Z naught to be like arbitrary and get us a general equation for a line. So R naught is just a point, but it's a vector that points at X naught, Y naught, Z naught. And T is a parameter. And we're calling it a parameter because we're kind of working from an XYZ space and getting all the XYZs in terms of one variable, T. So then we'd call T a parameter. If we have all those things, then here's the equation that you need to know. Our vector equation of a line, so that's what this is R naught plus TV. And if I pop in all those values that I just gave for V and for R naught, then what we end up with is a vector that has components X naught plus TA plus Y naught plus TB plus Z naught, sorry, not plus. The first component is X naught plus TA. The second component is Y naught plus TB. And the third component is Z naught plus TC. And all three of those together make up the vector equation of a line. Now, sometimes we just want a line segment. This equation right here gives an infinite line. That means it goes off forever in both directions. But if we just want a line segment, like from one point to another point, usually when they give points, the first point given is the one that is called your R naught. But you use P and Q, so you've got a line segment that starts at P, goes to Q, and your V vector will be the directed line segment, PQ. So the first point will give you your R naught, the directed line segment that you could build from PQ, that's going to be your direction vector. And then the last thing that has to happen is you put a domain on T, and it's always going to be, T goes from 0 to 1. And so here's what that looks like. It's very similar to what we see in the general form for an infinite line. It's just that instead of having our V vector with components A, B, and C, our V vector has components x1 minus x naught, y1 minus y naught, and z1 minus z naught. Those are going to be numbers. They're still going to be numbers, okay? And so this is our other form. I honestly only ever memorize the one that's for the infinite line. And I just know that if I have 2 points, I have to build a vector. That's my direction vector. And then I plop everything in. And if I'm dealing with a line segment, then I put the domain part on. And if I'm not dealing with a line segment, then I don't put the domain on. So this domain right here is needed to make it a finite line segment. Okay, so you're going to be asked for different forms for your lines, and there are 3 different forms. One of them is the vector equation, which we just went over. The next one, these are the parametric equations, and all we do is we use the idea that in any given vector, if you have a 3-dimensional vector, the first component is known as your x component. So anything that's in there, in that first component, is like an x of t, right? And then your second component is always your y component. So anything that's in there, whether it's a function or a number, is known as your y component. And then your third component is always known as your z component. So the parametric equations just explicitly state that, right? We take the first component that's in our vector equation and set it equal to x, because that is the x component. We do the same for y and the same for z. Now, if we were to take each of these parametric equations and solve for t in them, then what happens is we get the first one is t is equal to x minus x naught over a. And the second one, t is equal to y minus y naught over b. And the third one gives me t is equal to z minus z naught over c. And so all three of these representations are actually t, right? So that means all three of them are equal. So in the symmetric equations, we're like explicitly showing that symmetry in how when we solve for t in each of the components, we get a triple equivalent. Okay, so know the difference between the vector equation, the parametric equations, and the symmetric equations. Now, sometimes we'll be asked questions about whether our lines are parallel or they intersect. And so we have to know what we would do to determine if they're parallel or to determine if they intersect. And then we also need to know that if two lines are neither parallel nor intersecting, then we would call them skew because they're like they have no real relationship. Okay, so in order to know if two lines are parallel, we need to look at the direction vectors. Okay, so the direction vectors are parallel to the lines. And when we start talking about how are we going to test if two things are parallel, we have properties of vectors that would give us that information, but the line has like variables in it, right? It's got a t in it, so that kind of makes things more difficult. But if we remember that the direction vector is also parallel to the lines, then really we just need to examine the direction vectors. And if we can show that the direction vectors are parallel, then we know that the lines are parallel. And so what we have to remember is that the cross product of, if the cross product of two vectors is 0, then those two vectors must have been parallel. Okay? So it's like basically we're saying if V1 cross V2 is equal to the 0 vector, then V1 is parallel to V2. Okay? Now, if the cross product is not 0, we don't know anything. All we know is they're not parallel. Okay? Now, if we determine that two lines are parallel, then in a given question where we're being asked if the lines are parallel or intersecting or skew, if we just found that they're parallel, our work is done. But if we just found that they're not parallel, then we need to go on. We need to determine if the two lines intersect. So what we will do is we will give each line its own unique parameter. Remember the parameter word? That's the t. So for line 1, I would use the parameter t, and then maybe in line 2, I would use the parameter s. Okay, and then I'd have to set like components equal to each other, and I'd solve a system of 3 equations. If I can find an s and a t value that satisfy all 3 equations, then I know that the lines do intersect, and I can plug in the t and the s values to determine where they intersect. But if I cannot find a unique set of t and s values that satisfy all 3 components, then the lines do not intersect. And at that point, if we have neither parallel nor intersecting, then they must be skew. Okay? So we'll work through an example on that because that is a bit confusing. For now, let's get started on some problems. Remember, for any line, we need 2 things. We need R naught, remember that's a point, and V, which is a parallel vector. Okay? And we've got a line that is through the points -5, 2, 5, and 1, 6, -2. I'm going to go ahead and name these P and Q, just so I have something to call them. Okay? We can go ahead and let R naught be a vector pointing at P. That is, let R naught equal the vector -5, 2, 5. That will be a position vector that starts at the origin and ends at the point P. Okay, now we need a parallel vector. If we were to create a directed line segment out of P and Q, so we're going to create PQ, the directed line segment, then V is equal to the directed line segment, so and is parallel to the line. And I'm just going to put in parentheses, not on the line, just parallel. That's all we need. Okay, so I've already found my R naught. I need to create my V vector. V, again, is going to be the directed line segment, PQ. So we take the Q values and subtract the P values. That'll be 1 minus a -5, 6 minus 2, -2 minus 5. Go ahead and work those out. First component is 6, second component is 4, third component is -7. There's my V vector. Okay, I have everything I need. My vector equation is going to be R of t is equal to R naught plus TV. And I'm going to pop everything in here. R naught again was -5, 2, 5, plus t times v, which is 6, 4, -7. And then I just need to do one more rewrite on this to bring everything into one vector or angle brackets, set of angle brackets. So the first component will be -5 plus 6t. The second component will be 2 plus 4t. The third component will be 5 minus 7t. And that's my vector equation. We were asked to get the vector equations, parametric equations, and symmetric equations. They actually asked it in the opposite order, and that can be confusing because you actually need to get the vector equation first. Then you get the parametric equations. And the parametric equations are the easiest thing because all we do is take the first component of our vector equation and call it x. So x is equal to -5 plus 6t. We take the second component and call it y. Y is equal to 2 plus 4t. We take the third component and call it z. Z is equal to 5 minus 7t. That's it. Symmetric equations require us to solve for t in each of the parametric equations. So when we do that, in the first of them, if I solve for t, I get t is equal to x plus 5 over 6. So I just added the 5 and divided by 6. The second component tells me t is equal to y minus 2 over 4. The third component tells me t is equal to z minus 5 over -7. And then we typically don't actually write the whole t equals part because I have 3 unique things and they're all equal to t, which means those unique things are equal to each other. So what you would see is t is equal to x plus 5 over 6, which is equal to y minus 2 over 4, which is equal to z minus 5 over -7. And these 3 together are the symmetric equations. Okay, so let's just put boxes around what actually is what you're being asked for. Okay, so we had to create our parallel vector. We got our point for free. Sometimes you're going to have to do some work in order to come up with these. So let's look at another one. In this example, we're told to find a line through the point -6, 2, 3, and it is perpendicular to both of the next two vectors, 1, 1, 0 and 0, 1, 1. So first I need R0, and they gave me a point. They're telling me that my line goes through a point. So that is going to be the point that my R0 is pointing at, okay? So R0 is equal to the vector with components -6, 2, and 3. All right, now we just learned this, but we have to remember it. If we take two vectors and our line is perpendicular to both of them, let's just look and see what that looks at. I'm going to draw arbitrary vectors, okay? Let's say I've got this one and this one, okay? Now, I'm actually going to draw those from a different frame of reference. Something like that. Okay. Our line is perpendicular to both of these. Okay, that's kind of the best I can do in drawing these. So this is our line. We have to remember that the cross product of two vectors gives a vector that is perpendicular to each of the vectors. I'm going to call these A and B. Okay. If I was to find the cross product of A and B, I would get a vector that is perpendicular to both A and B. So let's see, A cross B is perpendicular to A and B. The line, our line that we're trying to find, is also perpendicular to A and B. What this means is that A cross B is parallel to our line. And what that means is that the direction vector of our line is parallel to A cross B. So V is parallel to A cross B. Now we need a vector, we need a direction vector that is parallel to our line. And we actually don't have a direction vector. And they didn't really give us enough information to just find one other than to use A cross B as V, our direction vector. I realize that's kind of a long and drawn out explanation, but some of you are going to get this more easily and some of you are going to really struggle with this concept. So I want to make sure that it's very clear. I often use pens and pencils to help myself to actually see what the situation is and what I need to do to find my parallel vector or my point. So based on that explanation, I need V, and I'm going to, so like up here I said let R0, down here I'm going to say let V equal the cross product of A and B. Well, that means I need to find the cross product. So I'll go ahead and write that out. I have my I, my J, my K. I have 1, 1, 0, and 0, 1, 1. When I calculate this, I get an I hat, 1 minus 0, minus J hat, and that'll be 1 minus 0, plus K hat, and that'll be 1 minus 0. So this all together is 1, negative 1, 1. That's my v vector. Okay, I should be able to build up my vector equation. R of t is equal to R naught plus t v. So I plug in my R naught. It is negative 6, 2, 3 plus t times the v vector I found, 1, negative 1, 1. And I just go ahead and combine those two vectors to make 1. So this will give me a vector with components negative 6 plus t, 2 minus t, and 3 plus t. And that is all. I can put a box around that and call it a day. Okay, so that one we had to go hunting a little bit, and that's kind of what you should expect in the homework, is that it won't just be here's a point, here's a parallel vector, plop it in. You're gonna have to find them. Okay, so use a little bit of creativity and imagination in order to do so. In this next problem, we're supposed to show that two lines are skew, and the way to do that is we have to show that they are not parallel and that they do not intersect. Okay, so to do this, we must show L1 and L2 are not parallel and do not intersect. Okay, so first part is the parallel part. Parallel lines, well, if V1 crossed with V2 does not equal the zero vector, then the lines are not parallel. What the heck are V1 and V2? Well, let's see. So for L1, L1 has an R naught and it has a V. If I was to write L1, so right now everything's given to me in parametric form, but if I was to write this out, R of t is equal to a vector with components 1 plus t, negative 2 plus 3t, and 4 minus t. And the numbers that are in front of the t values, those numbers make up the components of my v vector. So that's R1 of t, and V1 is equal to the vector with components 1, 3, and negative 1. So that's my slope vector. L2 has a vector equation. It's going to be, we'll call it R2 of s. And if I was to write it in vector equation form, the first component is 2s, the second is 3 plus s, the third is negative 3 plus 4s. Again, I'm going to identify my direction vector as v2, and it is made up of the components where I'm taking the coefficients in front of the s's in each component. So from the first one I get a 2, the second one I get a 1, the third one I get a 4. Okay, now that I have those pieces, I can go ahead and see if the cross product is equal to 0 or not. So V1 cross V2 is equal to I, J, K, 1, 3, negative 1, 2, 1, 4. This gives me I hat with a 3, negative 1, 1, 4, minus j hat with a 1, negative 1, 2, 4, plus k hat with a 1, 3, 2, 1. Working this out, I have I hat times 12 plus 1 minus j hat times 4 plus 2 plus k hat times 1 minus 6. I'm not even going to bother going any further with this. This is not the zero vector, and so the lines are not parallel. Okay, so I got to make a conclusion statement on there. I got that the cross product is non-zero, therefore the lines are not parallel. But now we have to show that they don't intersect as well. So the way to do this, I'm going to move to the next page. To find an intersection of L1 and L2, we will set components equal to each other and try to find a T and S value that satisfy all three equations. Okay, so the first equation we get is setting the x components equal to each other. So we get 1 plus t is equal to 2s. All right, the second equation comes from setting the y components equal to each other. So we get a negative 2 plus 3t is equal to 3 plus s. And the third equation is setting the z components equal to each other. So we get 4 minus t is equal to negative 3 plus 4s. All right, in the first equation, it's very simple to just solve for t. T is equal to 2s minus 1. Okay, I'm going to sub this into 2 and see what ends up happening. So if I sub it into 2, I'm going to get negative 2 plus 3 times 2s minus 1 is equal to 3 plus s. Negative 2 plus 6s minus 3 is equal to 3 plus s. Moving all the numbers over to the right and the s's to the left, I have 5s is equal to 8. So s is equal to 8/5. I'm going to take that s and substitute it back into t. T is equal to 2 times 8/5 minus 1, which gives me 16/5 minus 5/5. T is equal to 11/5. Okay, so those are the s and t values that work for equations 1 and 2. And that can actually lead you to think that we found a solution. We have to check these in equation 3. So we have to check t equals 11/5 and s equals 8/5 in here. So if I plug these in, I get 4 minus 11/5 is equal to negative 3 plus 4 times 8/5. On the left, I can rewrite that as 20 minus 11/5. And then on the right, I can rewrite that as negative 15 plus 32/5. So this is saying 9/5 is equal to, what is that, 17/5? Which is a very false statement. Okay? So my conclusion is that the lines are skew because they are not parallel or intersecting. Okay, that's kind of a long problem, and there's more than one thing to do in here. So definitely practice this one and practice the one that's in the homework. Make sure you're comfortable with it. So there are more questions about lines, but this kind of gives you a good introduction to it. And your homework, of course, will take you through more. Let's look at planes. A plane is pretty complicated because you can't just use one single parallel vector in order to determine the slant in space like you could with a line. If you imagine a plane to be like a piece of paper, okay, take a piece of paper and drop like 6 different pencils onto it in different directions. Every single one of the pencils is now parallel to your plane, right? But they're all pointing in different directions, which means no one pencil can determine how a plane slants in space. We need more than that. And it turns out that what we can do is we could take 2 vectors or pencils, we'll call them vectors for now. We could take 2 vectors that are parallel to our plane. And any 2 vectors that we take, if we found their cross product, it would give us a perpendicular vector to our plane. And it turns out that perpendicular vector will be able to give us a proper slope in the X, Y, and Z directions. That's kind of weird, right? But try it for yourself. Like take a piece of paper, take a pencil, make the pencil perpendicular to your paper, and then turn it in all sorts of directions. And notice, like, no matter how you turn your paper, that pencil's perpendicular to your paper. And as that perpendicular pencil changes its slopes, it's still maintaining the same relationship with the plane. So the normal vector or perpendicular vector is the one that's going to help us here. Okay, now there's a few new words in here. A normal vector is a vector which is orthogonal or perpendicular to a surface. So that's one of the things that we need, but you need to know the vocabulary. Whenever you see the word normal equals orthogonal is equal to perpendicular. We end up using different names depending on the space that we're working with and the object that we're working with. And so you're going to see this constant switch between orthogonal and normal. You're rarely going to see the word perpendicular, but it's fine if you use the word perpendicular because I think we all do still understand the meaning of perpendicular. Just get used to normal and orthogonal. Now in this picture that I have here, it's showing us a plane, and it's showing us that again, we need a vector that points to a point on our plane. So that's going to be the r naught vector that's right here. R naught is pointing to some x naught, y naught, z naught on the plane. And then we need another vector, r, and r is just arbitrary. It's any x, y, z point that is on the plane, okay? Now, if I was to take the r and the r naught and create a vector, so by taking r minus r naught, what that's going to give me is x minus x naught, y minus y naught, and z minus z naught. And that vector is parallel to the plane. While n, which we could say it has values a, b, and c, is perpendicular to the plane. And we learned back in 12.3 that if the dot product of 2 vectors is 0, then the vectors are perpendicular. And we learned also the reverse, that 2 perpendicular vectors in a dot product will give you 0. So since n and r minus r naught our perpendicular, we have the n dotted with r minus r naught will be equal to 0. Remember, dot product gives you a scalar, so that's 0, the number, not the vector. And this right here is the vector equation for a plane. Super important, okay? It's how we build our planes in 3-space. So once we have, I talk about this down below as well. But now that we've got that built, if we were to go ahead and take that dot product, we need to put in the components for n and the components for r minus r naught. And then we perform the dot product right here. That's the result after taking the dot product. Remember, A, B, and C are numbers. X naught, Y naught, and Z naught are all numbers. But the X, Y, and Z, those are the variables, and we need them to stay A, X, Y, and Z. Okay, so we can move all the constants to the right-hand side of the equal sign. That would be over here. These are all constants. And these over here, these are all the variables. And then we would have the equation of our plane. Okay, and that's the standard form for the scalar notation for a plane, as opposed to the vector notation for a plane. Okay, so in summary, what you need to know, okay, let's boil it down to something simple. Anytime you are asked for the equation of a line, you need to know that you need a point, r naught, and you need a parallel vector, v, and that the form of your line is r is equal to r naught plus tv. That's what you have to remember. If you're dealing with planes, actually before I say planes, if you're dealing with a line segment, you're going to throw a domain on that line that you just came up with in order to make sure it doesn't go beyond the 2 points. If you're dealing with planes, you need a point again, r naught. I forgot to put a hat on my r naught. Let me go ahead and put it there. And then we also need a perpendicular vector, okay? Once we have that perpendicular vector and we have our point, we have that the vector equation of our plane is the normal vector n dotted with r minus r naught is equal to 0. And then we're done. So let's look at some examples. Find the plane through the origin and perpendicular to the line. Okay, let's see what that means. All right, so we have a plane. Here's our plane. For lack of creativity, I'm drawing a flat plane, okay? And it goes through the origin. Maybe I'll draw a slanted plane. Sorry. I guess no matter how I draw it, it looks like it's flat because I'm drawing it on a piece of paper. All right, so this is going through the origin. Let's just draw this here. Okay. That means on the origin is on our plane. That's the point 0, 0, 0. So that tells me that r naught should be 0, 0, 0. Like, why not? That's easy, okay? But now we're also being told that there's this line out here, and this line is perpendicular to our plane. They actually say the plane is perpendicular to the line. It's the same thing. So we have this line. Let's actually draw that like this. So we're going to go. So this is the perpendicular line. Okay. Now the line has a direction vector, right? It has to have a direction vector, and that direction vector, I'm going to draw it on the line just so we can see it right there. That's v. Okay, that's the direction vector for our line. It's parallel to our line. And since it's parallel to our line, and our line is perpendicular to our plane. That means that the direction vector is also perpendicular to our plane. So that means we have a really great candidate for a normal vector. So we should go ahead and let our normal vector equal the direction vector from the given line. Okay, so let's figure out what that is. These numbers in front of t, the -8, the -7, and the 2, those are the components of v. V is equal to, I want n to be equal to v, and v has components -8, -7, and 2. Okay, and then I could just let, x, y, z be any other point on my graph, and then the book is telling me that I should go ahead and create a vector, the r minus the r naught. Okay, that's the geometric description, so we kind of have a better idea of what the heck is going on here. Now, we know the normal vector dotted with r minus r naught should equal 0. So let's pop those in there. The normal vector is -8, -7, 2. We're dotting it with x minus 0, y minus 0, z minus 0, and that should give us a result of 0. Okay? Now, doing the dot product gives us -8 times x minus 0. I'll stop writing the minus zeros in a moment. -7 times y minus 0 plus 2 times z minus 0 is equal to 0. Distribute and stop writing the zeros. We get -8x minus 7y plus 2z is equal to 0. And this is the equation of the plane. So this is our scalar equation, and this right here was our vector equation of the plane. Typically, you only have to give your scalar equation, but you get there from the vector equation. Okay, next example. Find the plane that contains the line that's given. We're given some parametric equations for a line, and it is parallel to another plane. Okay, so here's what we have here. Here's our plane. And we are told that there is a line that is on our plane. We are also told that there is another plane out there in the world that is parallel to our plane. Okay. The parallel plane has a normal vector. And let's go back and look at some stuff really quick. So remember in this previous problem, the normal vector was -8, -7, 2. Notice that the -8, the -7, and the 2 ended up as the coefficients for x, y, and z respectively. Also notice in the general form up here, when a, b, c was the vector for the normal vector, the components of our normal vector, a, b, and c, ended up being the coefficients in front of x, y, and z. So that means we should be able to go backwards. Like if we know the coefficients in front of x, y, and z for a plane, then we know the normal vector. Let's use that. So in this problem, that means that the normal vector has components 5, 2, and 1. And I'm just taking that straight from the plane that they gave us. Okay? Now, if that normal vector was to continue infinitely up, it would go through our plane and be perpendicular to our plane, which is what we want. So we're going to use n equals 5, 2, 1, since it is perpendicular to our plane. Okay, for R naught, we have a little bit of work to do. We have a line and it's on our plane. That means every single point of the line is also on the plane for every t value. So we should just be able to choose a t value and then find a point. So we're going to let t equal, honestly, you can choose any number you want. There's nothing special about me saying let t equal 1 at all. You could choose t equals 0. You could choose t equals pi. It doesn't matter, okay? Just a number. For R naught, we're going to let t equal 1. Then x is equal to 1 plus 1, which is 2. Y is equal to 2 minus 1, which is 1. And z is equal to 4 minus 3, which is 1. So R naught has components 2, 1, 1. All right, we have our R naught, we have our n. We can go straight to our vector equation. N dotted with r minus r naught is equal to 0. Plop those in. We have 5, 2, 1 dotted with x minus x naught, that'll be x minus 2. Y minus y naught, that'll be y minus 1. Z minus z naught will be z minus 1. And that should be a dot product equal to 0. Go ahead and do the dot product. We have 5 times x minus 2 plus 2 times y minus 1 plus 1 times z minus 1 is equal to 0. Now distribute. 5x minus 10 plus 2y minus 2 plus z minus 1 is 0. Combine and move all your numbers over to the other side. So on the left side, we have variables 5x plus 2y plus z. Our numbers, negative 10, negative 2, negative 1, that's a negative 13. And when I move it to the other side, it's a positive 13. And that is the equation of our plane. Okay. Now, I am at 52 minutes on this video, and I have 1, 2, 3 more problems to do. So I'm going to go ahead and stop this one and make one more video. I don't want it to cut off in the middle. So this concludes part 1.